Hello, everyone. This week we wanted to go over some questions and answers that had to do with your homework problems from last week. And these homework problems have to do with algebraic reasoning, graphing, and connections with geometry. My name is Destiny Clowers, and now I want to introduce to you guys my algebros.
I'm Jared Homshack.
I'm Andrew Brown.
Awesome. So we're going to go ahead and just jump right on into the questions. So this first one is for you, Jared. Is it important to try and create specific number values for the x and y axis?
This, first of all, good question. And this is referring to the first question on the quiz about the graphs and hypothetical scenarios. And in that case, I'd say no. You don't need to worry about values. The main thing you want to understand is general concepts. Like, for example, with the elevator graph I've got here on the right, I focused on identifying what we should label each axis based on the graph. Like, notice how the line constantly goes up at intervals? That's what I recognized we could represent that as the floor is traversed. And likewise, with the x-axis, it's the total amount of times it's always staying still. So the key here with that is just to look at the graph and say to yourself, okay, how could this line represent the scenario? And think about the scenario in of itself and think, okay, what happens in that scenario? Once you get that and figure out a way to label it, you'll have this question pat down. All right. Thank you for asking. Now let me ask you a question. Can you explain what both the x and y axis represents in this graph?
Sure. The x and y axis will be easier to imagine if you imagine this graph being the path that a bouncy ball takes while dropping off of a table. You can see in this graph that as x is increasing, y is slowly decreasing. You can know this by just looking at the first arch. That represents the first time that the ball hit the ground and bounced back into the air. It's much bigger and taller than the rest of the arches. So we can tell from this graph that the arches are getting shorter with each bounce. With that being said, x must represent the time that the bouncy ball is bouncing, while y represents the height of the bouncy ball. This means that the longer the ball bounces, the shorter the height gets. Andrew, speaking of this graph, how can you tell if it is truly a function or not?
Well, the definition of a function actually requires that only one y value be assigned to each x value. So this means that there can only be one answer to any question that involves a function. In this case, the vertical line test can always be counted on to tell you whether or not a graph is truly a function. You can see that the three vertical lines that I randomly placed on this graph only intersect the graph just once. This means that the graph is indeed a function since the vertical lines don't intersect the graph more than once. So thanks for asking me this question. I want to ask you a question. How am I supposed to interpret a graph without number values if the line doesn't even touch or cross the x-axis or origin?
Oh, that is an excellent question. Well, once again, it goes back about the scenarios. You just have to think about it and then figure out, okay, why would it not want to cross x-axis or origin? Like, for example, with the gas in the driving scenario, I have that over here on the right as well. If you have a car or truck, you never want to run out of gas. And based on our graph here, if we have our gas as the y value, then naturally we're not going to want that to cross over below the x-axis because that means we're out of gas. Not a good scenario. So just once again, think about the scenarios, and once you realize that there's a logical explanation for it, you won't really have to worry about this. So once again, just has to do with thinking about the scenario and wondering to yourself, okay, why would this happen, and why does it, in this case, not touch the x-axis? And then make the correlation. Once you have the labels pointed out to you in your mind, it'll make sense. Just, it'll work out. All right, Destiny, what are the variables in this chart here? Are there any in this problem?
Well, that is a great question. Variables are values in expressions that are subject to change. Depending on what number you plug into the variable, such as x, the value within the expression will change. In this problem, x is the variable. You can see that the numbers 0, 1, 2, and 3 were all plugged into x. So when we plugged x into our f of x function and our g of f of x function, the answer changed every single time. When x was equal to 0, our expression for f of x was 3 times 0, and the answer to that is 0. But when x was equal to 1, our expression was 3 times 1, and the answer to that was 3. You can see how the value of x changed each time throughout this graph when a different number was plugged into the variable. Thanks for asking.
You're welcome.
All right. How does this graph represent the functions f of x and g of f of x, Andrew?
So in order to determine how this graph represents both functions, let's try to understand each function and what is taking place. So the f of x is multiplying x by 3. The g of f of x is multiplying x by 3, and then adding 8. So for example, when x was equal to 0, f of x was equal to 0, because 3 times 0 equals 0. But g of f of x was equal to 8, because 3 times 0 plus 8 equals 8. So the variable of x was then changed to 1, 2, and 3 to also find the answers to f of x and g of f of x. This leads us to this graph. You can see how the graph represents the math that we just did for each function. The g of f of x line is shifted 8 units up from the f of x line, showing us that all we did was add 8 to every f of x input. So this means that no matter what the f of x input is, the g of f of x will always be shifted 8 units up on the graph.
Awesome.
So, yeah, thanks for asking that question. But I have a question for you, Jared. Is it possible to solve the function f of x by itself and use the answer to plug into the function of g of f of x?
Absolutely. As a matter of fact, this is kind of what I would actually did the first time I thought about this. Is I just started with f of x, and okay, that's 3x. So let's plug in 3. 3 times 3 is 9. So with that, you solved f of x when x is 3. Now instead of having to deal with the complication of f of x plus 8, you just plug in your answer here for f of x that you got, in this case 9, and plug it into g of f of x. So that just becomes f of x plus 8 is now 9 plus 8, which is 17, which is now demonstrated here on the graph in the orange portion. And once again, that also works with 2, because 3 times 2 is 6, and then you add 6 plus 8 to get 14. So once again, that also works. And this is how I would actually prefer to do it, especially when the equations get more complex. If this were like 3x squared plus 9, then it would be much more complex to plug that in, 3x squared plus 9 plus 8, than it is to just solve it on its own. It'll be much easier to solve a more complex equation like that on its own, and then plug it in to the second equation. But for a simpler problem like this, the method of f of x plus 8 does work, but doing the equations and the formulas on their own as independent steps does work better for me personally. Thank you for asking that. Now, Destiny, how exactly do you find the slope of a line?
Well, that's another great question, Jared. When given 2 points, the slope of the line that passes through those 2 points can be determined by using the slope formula. Now the slope formula is posted, which is y2 minus y1 divided by x2 minus x1. Let's look at an example with the given points 5, 5, and 3, 1. The first thing that you'll do is plug in the given points into their correct places within the slope formula. Once you do this, you'll get 5 minus 1 divided by 5 minus 3. You'll do the subtraction within the formula, and your answer will be 4 over 2. And luckily, our fraction will simplify to just 2. So this means that the slope of our line is 2. And this means that you have just learned how to find the slope of a line. And you can use that formula for every single equation that you have when you're trying to find the slope of a line. It's universal, so you can use it anytime. Okay, Andrew, what is the rise over run method?
Well, the rise over run method, see, we discovered in the last question that the slope of this line is 2. This can also be written as 2 over 1. This means that the 2 is the rise while the 1 is the run. So if you start at the point 3, 1 and rise up 2 units and run over 1 unit, you'll run straight into the line. But from that point that you just ran into, you can follow the same steps and run directly into the point 5, 5. So this is a great checking method to make sure that you've calculated the slope correctly. So yeah, thanks for asking the question. Jared, I got another question for you, man.
Go for it.
Is it possible for a line such as the one in the problem 3b to have no slope?
That is correct. I've actually got that specific line pointed out for you here on the graph, the bottom right. And the key is this. You want to look for that curve, as Destiny and Andrew have pointed out, that line kind of sloped upward to the right. But with this line here, you could see the points actually both sit on the value of x equals 5, which means the only way this thing can go is upwards and downwards. Likewise, if they both shared a same y value, such as y equals 5, then it would also just be going left to right. Now, in that case, there is no slope because there is no curve to the line. It's just going in a singular direction. And that's either called a no slope or zero slope. And that's depending on whether your x value or your y value is consistent. Thank you for that question. Now, Destiny, what kind of shift takes place among these graphs?
Well, as you can see, the graph of y equals x squared plus 7 is the graph of y equals x squared, but it's just shifted up 7 units. In the same way, the graph of y equals x squared minus 7 is the same graph as y equals x squared, shifted down 7 units. You can see that the graphs are either moving up or down along the y-axis. We know from past knowledge that the x-axis moves horizontally while the y-axis moves vertically. Therefore, these graphs are vertical shifts of the exact same curve. Andrew, how do you create a table of values in order to graph these 3 parabolas that we saw in the last problem? Oh.
We lost them.
Sorry, you guys, we had a little bit of a technical difficulty, but we're back.
So just to answer that question, to make a table of values for the first equation, y equals x2, we begin by plugging in random numbers for x. So you can actually pick any numbers to plug into x. So sometimes it's easier to pick smaller numbers that are for sure on your graph. So I chose to plug in -2, -1, 0, 1, and 2 for x. Then you use these points to graph the equation on a Cartesian coordinate plane. So after that, you'll make a table of values for the second equation, y equals x2 plus 7. And the third equation, y equals x2 minus 7. You can even use the same numbers to plug in for x. And lastly, you'll use these points to graph the equations on the same coordinate plane as the first equation. And there you have it. So I have a question for you, Jared. Can you explain how the graph of y equals x over 2 can be shifted up or down by using addition and subtraction?
Of course. All right, so let's start with one thing. We have a base equation here in y equals x squared. That's kind of the base of what we're doing here. Notice how one value you start with 1, go to 4, go to 9, 16, and 25, both directions. So that's kind of your gap here. You're going from 1 digit to 3 digits to 5 digits to 7 digits to 5 digits up in what is going to be your y value in the equation y equals x squared. Now, to add or subtract, note that we are not changing the equation y equals x squared. That is a constant in all three of the graphs. The difference is we're adding 7 or taking away 7 in the final product of what comes out of x squared. So say we do 1, x is still 1, 1 squared is still 1, but we either add 7 or take away 7. So it's still the same thing though. You go from 7 to 8, that's a gap of 1, 8 to 11 is a gap of 3, 11 to 16 is a gap of 5, 16 to 23 is 7, 23 to 32 is 9. Likewise, it's going to be the same here for minus 7. And you know what? Because those gaps between values are still going to be the same, it reflects here on the graph, because you'll see that the graphs are identical to each other in terms of the slope. The only difference is we are literally shifting the graph up or down. And as Destiny and Andrew have described, we either shift up by adding to the y value or shift down by taking away from the y value. So the key to remember, I have it labeled here in the hint, your plus and minus signs indicate a shift in the graph, with plus representing addition moving up on the y-axis and subtraction moving down on the y-axis. Good question. Back over to Destiny. What exactly is a perpendicular line?
A line is perpendicular to another line if and only if the two lines intersect at a right angle. This means that the two lines will only intersect once in a lifetime, and the point at which they intersect will be a perfect 90-degree angle. You can see in this graph that y equals 2x and y equals -1 over 2x are perpendicular because the slopes of these equations are negative reciprocals of each other. You can also see the square at the intersection of these two lines. That square represents a right angle that was formed because of the perpendicular lines. Thanks, Jared.
You're welcome.
Andrew, can you tell me how to find the negative reciprocal of a given slope?
Yeah. See, in order to find the negative reciprocal of a given slope, all you have to do is remember a few easy steps called flip and switch. In our example, we have a given slope of 3, which is also written as 3 over 1. The first step is taking the given slope of 3 over 1 and just flipping the numerator and the denominator. This now gives us 1 over 3. And after that, just switch the sign from positive and negative, and we now have our negative reciprocal of -1 over 3. So, yeah, thanks for the question, Jared. I have another question for you, man.
All right.
Could you provide an explanation of what the tangent of a line is supposed to represent?
Sure. A tangent line is one that crosses the boundary of an object or shape, but never actually gets into that said object or shape. If it's a line, it'll intersect it, but it won't cross over to the other side. Here with the circle, you demonstrate that by, I pointed it out here for y'all. You demonstrate that by running the line across, by touching one of the radiuses, but never actually going into the circle. And that really is the key thing. Tangent lines intersect an object, but they never cross or go into them. And to represent that here on the circle, you would intersect the radius, but never go into the circle. Demonstrate that and you'll do good. All right, Destiny, I got one last question for you. What is the radius of a circle?
I'm glad you asked. The radius of a circle is the distance from the center of a circle to one side of the same circle. In this example, the radius begins at the center, which is 0, 0. It then stretches to the other side of the circle, landing on 0, 9. This makes the radius 9. The radius could have been measured to any side of the circle, since any side would have given you the same distance of 9 units. Another way to think about the radius, though, is thinking of it as half the distance of the diameter. And Andrew, I want to ask you what the diameter of a circle is.
Okay. It's very simple. It's just like yours, but the diameter of a circle is the distance throughout the whole circle. It begins on one side of the circle and then moves straight past the center, and ends on the other side. So in this example, the diameter begins actually at -9 and passes through the center, ends at 9, positive 9. So this means that the diameter is 18 units long. You can also think of the diameter as 2 times the radius. So yeah, thank you for that question, Destiny.
Of course. I want to thank both of you for participating and asking questions and answering them. I hope that each of these questions and answers helped you all a little bit on last week's homework assignment. So the 3 of us are going to sign off, but we do thank y'all, and we hope that y'all have a great evening. Thank you.
Thank you.
See you next time.